example of a computer simulation where we have to put together the entire system, and then we need to enter it into the software and then have the software help us do the model, and then we go to MATLAB to do the analysis. So in the picture that you see here, you see a vehicle in here, car, you see a wall in here, and then this dummy is gonna crash into it. Your mission is to design the seat belts and the bumper of this car so that he doesn't get injured, and also that we are going to measure by not allowing that the seat belts would allow him to crash into the windshield over here, and also maintaining a certain force on him that would not injure him. So let's take a look at this as the problem statement here. So let's look at this dummy here. Say let's VW Rabbit here or any other car of that size. You have the following data. The seat belts must be treated to 3,000 pounds or 1,334 times 104 newtons. Yeah. The chest can sustain a force of 1,500 pounds distributed over 30 inches. You might recall that in the times where the seat belts were not so sophisticated, they were very wide. In fact, on my Chevrolet Impala 1969, one of those biggies, the seat belt, it's got two seat belts, and they are 4 inches wide. The newer ones are smaller because you have other factors that allow to distribute the load. In this case, the more area you had, the least the person could get injured. In that car, you have one shoulder strap, and of course, the lap strap is separate with the same idea to create bigger surface. So that's something to keep in mind. You cannot exceed the chest force of 1,500 pounds. El shoulder, the seat belt combination is 60 inches square. And in here we have a situation where you have this 1,500 kilograms is the mass of the car, and you have this is the seat belt in here for this. Oh no, this is the bumper here, B1, B. No, K1. Sorry, seat belt. And this is the mass of the person. It's 100 kilograms. Weights about 220, so it's big boy. And then we have the specification for K sub 2 and B sub 2, which are the for the bumpers. Okay. So in this case, you have, says the engineering model of this. We need to transform it into a computer model of this real car. We're going to do the computer model for doing simulation. What do we want to do? We want to make sure this is the design criteria, or you may say the constraints on your design. This simulation might produce a design for the seat belts and also for the bumper in such a way that the following optimal conditions will occur. The passenger should not hit the windshield if he travels at 25 or 55. We must control the force acting on the chest and the weight at 25 miles an hour or 55, and compare the data with the injuries and determine if the chest or internal injury occurs. If so, that situation must be avoided and you must change the design. That's the idea. If he wears the seat belt only, or if he wears the shoulder strap and the seat belt, and what is the force acting on this chest and waist at 25 miles an hour and at 55? Okay. So in this case, what's the critical maximum velocity when no injury occurs, when impact occurs? So hitting the windshield or chest injury, internal injury, seatbelt failures should not occur. Any of those things. So how are you going to know when this happens? When you run the program and you plot actually the force on the chest, that graph is going to give you the level that the force will reach. So if it is more than what's specified, you know that that thing is not working. You're going to plot also the distance that his head is from the windshield at all times. And if it goes past the limit of the distance that the program tells you, you know he's gone through the windshield at that point. Okay, so it has to be at that exact dimension. Otherwise, he has, even his nose might have gone through with the windshield. You don't want that. Also, let me put this scenario forward. The seat belt cannot be totally flexible because if it doesn't hold him, forget it. He's go through the windshield. The seat belt also can be totally rigid because it would be like you put a crowbar across him, cut him in half. So you see, it's a lot of things involved on this, and you can see how the in the safety of the new vehicles, the vehicle designers have been able to tune that system up so that the system won't hurt you. Because think about it, an airbag works with an explosion, basically. That's why, an airbag could also kill somebody, like a child, for example, because the forces are very high. So you don't want children riding in the front seat. That's why they're on the back. And for the adults, your seat belt needs to hold you enough so that you don't crash into the steering wheel or the windshield. So there has to be a little bit of a give, but I'm saying little bit because the new cars are designed in such a way that when the crash occurs, the seatbelt will tighten you instantaneously, but it will release you at the same time so that you don't get hurt. Okay, so those are the balances that we're going to face on this design. And here are some hints. Understand which variables represent the displacement of the head and the values to determine if his head hit the windshield. What's the maximum displacement? All those things. I'm suggesting to make a table like I show you in here. Yeah, you have a table in here where you have values of the different computer simulations. And then I'm giving you some guidance as to what your lab should look like. Explain the development of your computer model, and I would like you to take a look at the bond graph model approach, but also the block diagram model approach. So this is something that you want to get started as soon as possible and bring me questions the next class. So because there's going to be at least 2 classes before it's due, okay? So you have more than a week. But what I suggest is that you do not wait until next week to begin asking me. Try it now. Wrestle with it. You'll have some problems in there, and those are exactly the ones I would like to know. I would like to know those problems. Okay. Any comments or questions so far based on what I have told you? So that's their problem. This lab is going to be a bit of a handheld lab. So I am going to give you a guideline on how to do the model, how to enter it into ChemG, and what to expect, once you get the first results. So what you can do is, just as I am working the model here on the presentation, you could actually follow on your computer, and that way will save some time. So we'll go back here to our web page, and sorry, we needed to click over here, right there. Let's just go to the links of the class lectures, because that way you'll be able to get on to the tutorial that I have for this lab. Takes a little while to load the web page, huh? Okay, you're here on ME 171, which is right here. Okay, and what we want is to go to class notes in here, and in here let's go to the mechanical system. Okay, and I call it modeling step by step. Yeah. So here we go. We have this little card, a little more colorful in there, with the same specifications, everything I told you a moment ago. And what we need to do is to begin creating the bond graph model of this. This is the data, same data I gave you, and same conditions of the problem. But see, wouldn't it be nice if somehow we just look at the parts and put words? See, this is pretty straightforward. You have the wall over here on the left hand side. Yeah. You have the bumper here on this. You have the car seat belts right here and the dummy there. These are all the components of the system that we have. What I'm going to propose is this word bond graph, which is, I would say, is our logical guideline as to what the system is. We should follow some steps in here to be able to do this. The first step that I do is recognize the velocities of the system. Hmm? Mm-hmm. I'll see. Okay, here we go. So we have the velocity of the system, all the velocities of the system. Okay. So in this situation, you recognize this is just to build a skeleton for our model, and we use these one junctions to represent each distinct velocity of the system as our basic structure of the bond graph model. So in here we put all the one like the wall, for example. There's the dummy. There's the relative velocity between the wall and the car itself, and the relative velocity between the, the car and the person. But let's not concentrate on these ones, but only on these three for now. These ones, like that. So to those physical elements, okay, the velocity of the dummy here is represented by one junction, and the I element is the dummy itself. This one is like a source of flow with velocity 0, because the wall is just there. And this one is the velocity of the car. So one junctions first, then second one, put the elements that are attached to one junctions. And next we are going to do the velocities, the relative velocities in there. In fact, if you look at this thing here, what will happen is you have the velocity of the car minus the velocity of the wall is what this is. And the velocity of the car minus the velocity of the dummy is what the angular is what the seat belt is. So the difference in velocities are made with 0 junctions. And so we continue over here. We attach to the 0 junctions the elements that you see like the R and C, which is the seat belt, and the bumper on the other one over here. See? And this is how we put together the entire model. And so it looks like a bond graph model now that would be ready to put it into the CAMG software. So we can simplify the graph and make it look pretty But basically what you have is, let's see if we can point out in here the seat belts in here, the wall, the seat, no, the bumper here, the seat belts, the wall, and the car. Let's see if we could actually, yeah, there's the label still. There's the wall in here, there's the bumper over here, there's the seat belts, and there's the dummy. And so with this, we should be able to enter the into CAMG to do the computer simulation, and that we will analyze it in next lecture. So, okay, I'm going to go over here.